Hello, Professor. Uh, I'm Sricharan Cherepally, and this is my final presentation for automated casting defect detection. So, since the midterm, I properly turned my deep learning model, tested some assumptions I had been making, and double checked my results were correct, actually trustworthy. The short version, my simpler model was ahead at the midterm, but after real learning, the deep learning model ended up far ahead, and I made sure that the results actually holds up. So coming to the final architecture and design. So here is the whole system laid out. Every image goes through the same processing steps first, brightening, edge detection, and so on. From there, it splits into two parts. My simpler model, which measures texture patterns by hand, and my deep learning model, which learns patterns on its own. I kept both parts all the way through, even after the deep learning one pulled ahead, because having a simple, easy to explain baseline is valuable on its own. And coming to the next slide, which is the image analysis evaluation. So I went back and actually tested one of my assumptions from the pitch, that brightening the image before training would clearly help. It turned out the effect was small and mixed. It helped one model a little and actually hurt the other model slightly. That makes sense once you realize that the real signal was coming from the texture patterns, not from the brightening step. And coming to the next slide, which is the hyperparameter optimization. So from a deep learning model, I tried 5 different setups instead of just training it once. The biggest thing that mattered by far was letting the model adjust more of its internal settings instead of just a small part. That long jumped accuracy from about 93% to almost 100%. After that, using a bigger group of images per training step and training a bit longer, each gave a small extra boost on the top. Coming to the next slide, which is the data integrity check. So getting nearly 100% felt almost too good. So I checked for a common problem, whether any of my testing images had accidentally also ended up in my training data, which would let the model just memorize the answer instead of actually learning. I found out that about 9% of my testing images were exact duplicate that were also in training, all of them in the normal category. I removed them from the training and ran the tuning again from scratch. The accuracy held at basically the same very high number, which told me the results was real, not just an accident of the duplicate images. So coming to the results and metrics, so here is the full picture across the whole project. My simpler model both landed around 91 to 93%. My deep learning model started out worse at about 86%, which is, was barely trained, but after proper tuning, it jumped to nearly 100%, and that number held up even after I removed the duplicate images. That's the pattern other researchers found before me. So deep learning wins, but only once you actually train it properly. So coming to the visual demonstration. So this is a screenshot from my live demo, which is a separate video I am also submitting. In it, I run my model on 6 real images it's never seen before, one at a time, and show it prediction next to the correct answer as it happens. It got 5 out of 6 correct on live. I actually like that it wasn't a perfect 6 out of 6. It shows it is a real, honest run and not something stacked to look flawless. So, to wrap up on my conclusion, so my deep learning model ended up clearly beating my simpler model, exactly like the research I looked at earlier predicted. But only once I actually tuned it properly instead of just running it once. I made sure that nearly perfect result was trustworthy by checking for and removing a data problem before believing it. And throughout the project, I tried to trust my assumption directly instead of just assuming they were true. Final numbers, my simpler model got about 93% and my properly tuned deep learning model got 99.86%. Thank you.